Okay, this is for the Astronomy 320 lecture. It's July 28th. That's 7:56 p.m. at night. Okay, so we're only going to go through this one section here, 18.4, the HR diagram, Hertzsprung-Russell diagram. Just a few other things to point out here first. Okay, so I tried to schedule a Zoom meeting. This is the first time I've ever done it. So it's tomorrow from 10:30 to 11:30. Okay, so it's a half hour, last half hour of our official class time, and then a half hour after that. And so I'll just be sitting here, hopefully. Okay, hopefully I'll figure out how this works tomorrow. But I at least got the meeting scheduled, so I think that's like the first step. Okay, so from 10:30 to 11:30, you can ask questions, I can go over stuff, whatever the case may be. Okay, so that's scheduled, and then over here in the modules, so we've got, here's the PowerPoint we're about to go over, so it's up there, and then here is the online worksheet we're about to go over. The online worksheet looks like this. Okay, so this is the one we're about to go over right now. Okay, so on the HR diagram, so basically, let me just go down and look at the diagram first. Okay, this is an example of an HR diagram. Here's a better one. All right, so what they're doing is they're graphing luminosity versus surface temperature, basically. We see spectral class. You got an OBA, FG, KM here. That's 25,000 Kelvin. It's 10,000 Kelvin, 6,000 Kelvin, right about here, 3,000 Kelvin. So the temperature decreases as we go left to right down here. So these are the temperatures of stars, and this is how luminous they appear. This would be absolute brightness, not apparent brightness. This would be absolute brightness, how bright they would appear if they were exactly 10 parsecs away. And Hertzsprung and Russell, are two people independently, discovered that there was a relationship between the luminosity and the surface temperature. Okay, so they made a graph of that. So up here, we've got O stars. They are the biggest. You see a number with them, so they're good enough to separate them into 1, 2, 3, 4, 5, 6, 7 classes. But then once we got better at observing stuff, they could see differences within the O, within the B, and so on. So they started making it O0 through O9. Okay, so let's just concentrate on the O stars. They are the hottest. They are the most luminous. Okay, the O stars. Then B, and it goes right down to M. M stars are the coolest, and look at that luminosity, very small. We go from 7 times 10 to the 5th, it looks like, down to 0.05. The sun's a G star, okay? I think it's actually a G6. We got a G0 star here. It's about 1.1 times the mass of the sun. It's about 1.4 times the luminosity of the sun. Its surface temperature is about the same as the sun. Sun's about 5,800 Kelvin. Okay, so that's how they have it. O stars 40,000, B stars 28,000. About this is, and it's specifically A0 stars or 10,000, F0 stars or 7,500. G stars, our sun is a G6. G0 would be about 6,000. Our sun's about 5,800. Then K stars would be 5,000, and M stars would be 3,500. So it's kind of like the same as if you went around and you did a graph of miles per gallon of different vehicles. You go out into, I don't know, parking lot or someplace, and you just look at all the vehicles that are sitting in this parking lot. It could go anywhere from motorcycles, which are very, very small, but get great gas mileage, all the way up to big, huge semi-trucks that are huge, big vehicle size, but don't get good gas mileage. And most cars, you know, you got your pickup trucks, you got your sedans, you got your hatchbacks, you got your whatever. They all would fall in along this sequence pretty much, that we see a relationship between vehicle size and gas mileage. Now there are outliers, okay, these are small vehicles, but they get bad gas mileage. So they could be like, I don't know, a Vega or a Gremlin from the 1970s that hasn't had a tune-up in 30 years and gets horrible gas mileage. Okay, that'd be a small vehicle with bad gas mileage. And you got like hybrids, like a hybrid Escalade. It's a big vehicle, maybe not as big as trucks, probably that one shouldn't be there, I don't know. But anyway, big vehicles, but they get good gas mileage because they're hybrids. Okay, so if we were going to make a graph of miles per gallon that a vehicle gets in its size, we may get something that looks like the graph to the right. Motorcycles are small and get good gas mileage. Trucks are large and get poor gas mileage. Most vehicles would fall along the line we call the main sequence. So there's the main sequence. So the vast majority of the cars you would run into would fall along that line right there. Okay, now here's an HR diagram. So these are the stars. We got main sequence stars. We got some other outliers here. Look at that. We got some white dwarfs, we call them, down here. We got these big, huge red supergiants out here. Okay, the Hertzsprung-Russell diagram, we're going to call it the HR diagram from now on, is a graph which Hertzsprung-Russell displays the relationship between luminosity of a star and its surface temperature. Okay, there's the surface temperature. They don't have the temperatures written down here. Remember, this is like 40,000, 30,000, 40,000, someplace in there, and this is like 3,000 down here. The temperature decreases from left to right. So O stars are the hottest and M stars are the coolest. More than 90% of stars lie along the main sequence. The main sequence stars are the ones still fusing, that should be fusing hydrogen into helium in the core. All right, so it should be, this should say fusing hydrogen into helium at the core. Okay, so we go over here to our online thing. What is graphed on the HR diagram? Luminosity versus surface temperature. Luminosity. This is luminosity, and then here, this will show it better. This is luminosity. Okay, one is the luminosity of the sun, so it would be someplace in here, versus surface temperature. So we got the surface temperature here, 25,000 down to 3,000. Okay, so that's what's being graphed on that thing. Okay, how is temperature displayed on the horizontal axis? It's displayed as decreasing from left to right, so it's opposite of what you might be familiar with. Okay, the numbers aren't increasing. The numbers aren't increasing from left to right. They didn't go 3,000 down here and 25,000 over here. They went 25,000 over here and 3,000 over here. So they're decreasing from left to right. Then, okay, along what are most stars found? They're found along the main sequence. In the main sequence, the stars have in common is they're all still fusing hydrogen into helium. So if we take a look at our main sequence again, they're fusing hydrogen into helium. These guys have run out of hydrogen and they're starting to fuse helium into carbon, for example. Our sun will get up here at some point. Okay, so the HR diagram, they move. Okay, so we covered everything here. Red giants are stars that have exhausted their hydrogen fuel in the core and have started to fuse helium. When this happens, their surface cools. So these guys used to be over here, but they cooled down. Their surface cooled. But they went up, didn't they? It looks like they might have gone up a little bit. These guys are kind of like going up into there. This happens when their surface cools, but they also expand. So expand means more area in which to emit energy. Okay, so you've cooled down, but you're emitting more energy. Okay, which means they become more luminous. They get bigger, so even though their surface temperature is decreased, there's more area with which to put out energy, so they get they get brighter. On the HR diagram, they move up to the right, cooler temperatures, and up more luminous. On the HR diagram, they move to the right towards the cooler temperatures, and up to the more luminous. There should be a parenthesis there. Okay, white dwarfs are the leftover core of stars like the sun. So most of these stars, ones that are less than 8 times the mass of the sun. So if you're I think that's the cutoff. If you're more than 8 times the mass of the sun, I believe it is, you're going to go supernova and blow up. But if you're less than 8 times the mass of the sun, you're going to have a very peaceful death. You're going to get to a point where you're going to become what's called planetary nebula, where the core no longer is able to produce any energy. We've got a carbon core, and the sun can't go beyond carbon because it doesn't have enough mass to produce the other types of nuclear reactions. And the outer layers just kind of blow off into space, leaving behind the core. So these are leftover cores from stars. Now they're very, very hot. Why? Because they're the leftover core. The sun's core is something like 600 million Kelvin, maybe. So the sun's core is very, very hot right now. So it's going to cool down over time, but it's still extremely hot. So it's still got very high temperatures, but it is so small. It's a leftover core. The outer layers have left. That it's not good. It's so small. It's not going to be very luminous. Maybe very, very hot, but it's very small. Okay, opposite of these guys. They may be cooler, but they're very, very big, so they become more luminous. Okay, White dwarfs are the leftover core of stars like the sun. They have extremely hot surface temperatures but are very small, and as a result they are not very luminous. Okay, let's see if we can answer some questions now. Okay, what do the main sequence stars, I think we did that one. They're still fusing hydrogen and helium. What are red giants? Okay, red giants are stars that were on the main sequence, but they've run out of hydrogen and now they're fusing helium into carbon for the most part. Where do we tend to find them on the HR diagram? Okay, we tend to find them in the upper right. Okay, so take a look. These are the red giants up here. These are in the upper right. Okay. Then, what are white dwarfs? Where do we tend to find them on the HR diagram? So white dwarfs are the leftover cores of stars that didn't have enough mass to go supernova, and they are found on the lower left. So the red giants are upper right, and then the white dwarfs are lower left. Okay, they're right there, lower left of the HR diagram. And then blue giants, now if we go back to the other picture, blue giants are still in the main sequence. Okay, blue giants are still in the main sequence. They're here, okay? These are main sequence stars and they're blue. So these are called the blue giants. Red giants have left the main sequence. Blue giants are still on the main sequence, but blue giants will eventually become red giants and go supernova in a lot of cases. We're expecting Betelgeuse, a red giant right now, to go supernova at any time. Betelgeuse used to be over here long before we came along, but it used to be over here. Okay, so it ran out of hydrogen and now it's fusing helium and other things into heavier elements through nuclear synthesis, and so it's over here now. It's not on the main sequence, but these are the blue giants. They're in the upper left. Okay, these guys down here are red dwarfs. I think we have a diagram that shows the red dwarfs. They're red dwarfs. Okay, they're on the main sequence as well, but they're very, very small. Okay, and they're very, very cool. They've got cool temperatures, like about 3,000 Kelvin. Just to give you an example of a question that I would ask, but I don't have enough. I don't know how to set this up. This is a year, well, sort of a year ago, July 16th, 2019. You can see we didn't go as fast as I have in the past because of this. No matter what people tell you, online learning is not anywhere near as good as in person. Okay, below is the below is an HR Russell diagram. So I would have to draw the diagram in here. Okay, but what I would do is I would take off the names red giant, red dwarf, blue giant, white dwarf, and whatever, and put letters in. Okay, so in other words, I could have had an A up here. Well, then you would circle for the blue giants, you would circle A. Then I could have had a B over here. So then for the red giants, you'd circle B, or that type of thing. So what I could do is say, on the upper right-hand corner of the HR diagram, we'd find which of the following. It'd be red giants, blue giants, red dwarfs, white dwarfs, that type of thing. The sun's right here. That's the other one we haven't run into yet. The sun's right there in the middle. Let's look at this. Okay, so along the main sequence, the largest stars are called blue giants. They're up here. Along the main sequence, the small stars are called the red dwarfs. They're down here. They're both still in the main sequence. The sun sits close to the middle. There's the sun right there. So the sun would be right about here. So there's one, and these are relative to the sun. So this guy's 100 times the luminosity of the sun. This is 10,000 times the luminosity of the sun. This is 0.01 times the luminosity of the sun. The red dwarfs are not very luminous. The sun would sit right about there. Okay, right in the middle of everything. Okay, so that's basically type of questions it would have there. And if we go down here, there's this guy, and then there's nothing, so we're done. Okay, so going over the questions again. What are red dwarfs? Blue giants are main sequence stars that are still on the main sequence because they still continue to fuse hydrogen and helium. It's just that they're very, very big. Red dwarfs are also right along the main sequence. They're very small, they're not very luminous, and they have cooler surface. Now it's 3,000 Kelvin, obviously, is where you're sitting right now. It's about 290 Kelvin, probably someplace in that. So obviously, they're still extremely hot, but we're talking in comparison to other stars. Where do we find the sun in the main sequence? Kind of like right in the middle of the main sequence. We find the sun right in the middle of the main sequence. We can see it on that last diagram. Here it is. The sun would be right there, kind of in the middle. Okay. So that is a 95, some huge number. 90% of the stars fall along the main sequence right in here. You got your white dwarfs and so on. Okay, so there's no more material. This is everything for the final on Thursday, and we got everything set up on. So you got your. This is the one we just looked at. Okay, and then I give you a place to turn in. Obviously, you just have to write down what I said and get your credit. Where is it? There it is. Okay, so you can turn it in right there. And then we got the newest, what I did, the PowerPoint I just went up over is right there. And I believe that is everything. Again, let me see what that com for Zoom. It is different from Sac State, so I'm not that confident. I got it to work at Sac State. I go com for Zoom. So I'll be here tomorrow. There it is. So hopefully tomorrow at 10:30 I can just click on that maybe. Maybe if I just click on that, it'll open it, and then I'll see who shows up. And again, I can go over stuff, and I think that's about everything. So I'll talk to you tomorrow maybe.